Okay, let's talk sports science from an exercise physiology perspective. So what I like to do whenever I start an area, I do like to define things so that we're all on the same page. I'm sure you know what exercise physiology is. It's a very common term, phrase, concept, whichever. But it is good to take a step back and just say, what is exercise physiology about? Well, exercise is a bodily exertion for the sake of developing and maintaining physical fitness. You go for a run, a swim, a bike, whatever it is. Physiology is a branch of biology that deals with the functions and activities of life or of living matter, such as organs, tissue, cells, and the physical and chemical phenomena involved. So in kinesiology, we do a lot of exercise physiology work of humans. We try to understand the physiological responses to exercise, the physiological responses during exercise. So we're trying to understand functions, activities, and so forth. So we're trying to understand the processes that allow us to exercise or how exercise influences those processes. When we start talking about when we start talking about exercise physiology, we're starting to get into the world of understanding energy systems, anaerobic and aerobic pathways, where we take fuels, carbohydrates, fats, maybe proteins too, a little bit, and we use those fuels to ultimately generate a force at a muscle that allows us to move. In terms like VO2 max, I'll go through this in this presentation, or respiratory exchange ratio, which is the ratio of carbon dioxide exhaled to oxygen used, or terms like lactate threshold or anaerobic threshold or training adaptations. These things all come to mind when we start looking or thinking as exercise physiologists. So when we start talking about energy, we got to understand that there's different forms of energy. And energy is the capacity to do work. From a physics perspective, work is applying a force over some distance. So it involves some type of movement, if you will. And there's different forms of energy: nuclear, heat, mechanical, chemical, light. And oh, wow, that's weird. My slide is showing. There's the definition of energy as the capacity to do work. That's out of order, but that's okay. And the units of energy are units of joules. Now, work is the transfer of energy from one object to another. Okay, and as I just said, mechanical work is the application of a force over some distance. And so what we're doing is we're transforming energy from an object to another, or from one form of energy to another form of energy. Now, a term that's closely associated with this is calorie. Calorie is a unit of heat. 1 calorie is equal to 4,184 joules. So these are equivalent units. They're just different magnitudes, like miles versus kilometers. And we have this phrase called large calorie of kilocalories. So a calorie is the amount of heat needed to change the temperature of 1 kilogram of water, 1 liter of water, that is, from 14.5 degrees Celsius to 15.5 degrees Celsius. That's a very specific measurement. In essence, calorie is a measurement of heat. So if the energy were released of a substance with a caloric value of 300 calories, this is what that means. It means the temperature of 300 liters of water would be raised 1 degree Celsius. All right, and so this is what we're ultimately talking about when we look at a fuel, a food. We look at a label and you see the calories there. That is telling us how much potential energy that fuel, that food has. So I use this model. I've presented this in other presentations, and it's something that sort of helps me summarize a lot of different things when I'm talking about human movement or human performance. So on the left side is we have chemical energy in the body. Energy is the capacity to do work. In this case, it's really potential chemical energy, because the energy's in me now. I've got fat, I've got carbohydrates stored in my body. There's the potential to use those fuels to transform into another form of energy to allow movement. Just like a car, the car is always an easy analogy, in that we put gas in our car, or if you got an electric car, you charge up your battery, and that has potential electric energy in that case, or potential chemical energy in the case if you put fuel in gas in the engine or in the tank. That has the capacity to do work. The engine is going to ultimately transform that capacity or that potential chemical energy to mechanical energy that allows the car engine to ultimately power the wheels. And same thing in the human body. We have an engine in us. We have different engines, if you will, or hybrid, where we can transform chemical energy using different metabolic pathways to ultimately generate or create mechanical energy. So we're transforming chemical energy to mechanical energy. Now, one rule of thermoregulation is that we can't ever create nor destroy energy. So whatever transformation of energy there is at this moment in time, there's going to be the same amount of energy over in this moment in time. However, when we look at the actual potential chemical energy in the body and the resultant mechanical energy, there's never a one-for-one match. We never perfectly transform this energy to this energy. In fact, we typically only transform about 25% of the chemical energy to mechanical energy. Where's the other 75% of energy go? Well, that goes off pretty much in the form of heat, all right, which is a unit of calorie. And so that heat will enter back in when we start trying to understand this transformation from energy in one state to another state. We can actually measure the heat to understand how much transformation of energy has actually happened. I'll talk about that in just a little bit. So in chemical energy, from an exercise physiology perspective, we've got fuels in the body, we've got storage of fuels, and we concern ourselves with fuel intake before, during, and after exercise or an event or what have you. This is a very exercise physiologist sort of perspective of what's happening, looking at aerobic and anaerobic pathways, transforming chemical energy to mechanical energy with the use of oxygen and without the use of oxygen. So aerobic with, anaerobic without. And we need to understand training elements, frequency, intensity, and time in terms of how that might train each of these systems to better transform chemical energy to mechanical energy, either more of it or faster. We also want to concern ourselves with monitoring training by monitoring things like heart rate, maybe power, rating of perceived exertion, which is a psychological metric, a psychometric, or maybe even look at lactic acid or a number of other metrics that can be monitored for training and the stress that we're imposing to the body. And we really want to pay attention to thermoregulation. As I said, 75% of the energy in this chemical energy is not being transformed to mechanical energy. It's generating heat. And sometimes we want to retain that heat if we're exercising in the cold, or we want to get rid of that heat if we're exercising in a hot environment. And I got this down here, injury too much, too soon, too fast, because we are monitoring training and keeping our eye on that. We want to be careful to be able to train without injury, because once we're injured, we interfere with the whole training process. And over here, mechanical energy, this part is more in the biomechanics world, where we're looking at force generation of a muscle, and we're looking at the magnitude of force, the direction of forces being applied, and we're looking at coordination of forces between different muscles. And we start looking at things like resistance forces, or looking at, learning to generate the right amount of force, apply it in the right direction, and applied it at the right moment in time. So we're doing things like drills, we're looking at technique, we're trying to understand equipment, things like that. So exercise physiology is more centered in this transformation process of chemical to mechanical energy, but exercise physiology does blend over here to chemical energy and does blend over here to mechanical energy as well, but more centric in this model. So when we talk about exercise physiology, as I mentioned, we are really interested in the metabolic pathways and understanding those You should have, by the time they're taking this course, had an exposure to aerobic pathways and anaerobic pathways in different courses. So my intent is not to teach you these pathways, but you need to understand the different pathways and the different details of some of the pathways. For example, anaerobic pathways generate ATP, and I'm expecting that you understand what ATP is. It's adenosine triphosphate, and this is what allows muscle contraction to occur. And so generation of ATP is critical to generating a muscle force, which ultimately is critical with generating movement. And anaerobic pathways, there's just a simple, there's a combination of phosphocreatine and adenosine diphosphate to create ATP, and then that ATP is used to generate force. There's a anaerobic pathway of taking carbohydrate or glycogen and transforming that down to ultimately lactate. And along the way, we pick up some ATP in this process. And then this is just a schematic of creating ATP. And so we have phosphocreatine or creatine phosphate pathway. We have glycolysis pathway. These are pathways to generate ATP without the need of oxygen. Aerobic pathways, in these pathways, there's different pathways for protein, for carbohydrates, and for fats. And you should have learned each of these pathways in an exercise physiology or maybe anatomy and physiology classes even. This process, or these processes, all these steps, happen within the mitochondria of a muscle and all require oxygen. But oxygen is not needed until the very last step. And so this process of glycolysis up here outside the mitochondria is the same process as happening over here. Here's pyruvate. If certain coenzymes are available, that pyruvate gets pulled into the mitochondria, and then aerobic steps of generating ATP all happen seamlessly. If coenzymes are not available to pull pyruvate into the mitochondria, then lactate is produced, and this process over here continues. So glycolysis is the same anaerobic part that's over here. And triglycerides, these are big molecules. These are substances that generate a lot of that ATP. Beta oxidation is the process. And there's a lot of steps involved with breaking fats down ultimately to ATP. The advantages of using fats as a fuel is you generate a lot of ATP. It just is that there's more steps involved, and so it's a slower process than something like the aerobic breakdown of carbohydrate. So evaluating metabolic pathways. In sports science, we typically want to know how well these two pathways are working, or how much or how active these pathways are working. And so we have several different protocols or different tests that we can use to determine the activity of different pathways. We also have some different biomarkers that we can measure to try to get a sense for some of the activity of these pathways. In the anaerobic world, we use a Wingate anaerobic test, which is an all-out 30-second bike test. You sit on the bike and you just go all out for 30 seconds. We have a vertical jump test, see how high you can jump from a standing posture. We have a 300-yard shuttle run. We have isokinetic testing. We have other strength testing, 1RM, 3RM, other iterations of that type of strength measurement. We can also measure blood lactate during different tests or different evaluations, and others. So this is not an exhaustive list at all. We also have tests to determine how active the aerobic pathway is by looking at a graded exercise test. I'm going to talk about that in a second. A 12-minute run is very common. Step tests for time or keeping a cadence is another one. A 1-mile walk is a way to evaluate the aerobic pathway. And we're often looking to measure metabolic measurements like how much oxygen is being used or how much carbon dioxide is being exhaled. And there's other tests as well. But as a sports scientist, we can lean on our exercise physiology lens and try to come up with different ways to evaluate the metabolic pathways that are present or active in different stages of training or in different activities. So with 4x point, and one of the things we need to look at when we are picking those tests is the time of the test. So if we're looking to test the anaerobic system, we're looking at doing tests that are very short duration. 1 hour, 1 RM, strength bench press, or vertical jump test, that happens fast. 40-meter sprint, that's a very short, 4, 5, 6 second type of test. And so this is just a graph of how active each energy system is, and this on the x-axis is how long the activity lasts. And so for the shorter duration, less than 100-second test, the ATP-CP, the creatine phosphate pathway, is very active. The glycolysis is active up to about 300 seconds, and these are ballpark numbers. It's not going to be the same for everybody or different points in time of a training program. And then if we're trying to evaluate the aerobic pathway, we're doing tests that are taking longer than 5 minutes. And so when we're trying to match up our understanding of pathways with our tests, we're trying to keep this exercise physiology principle of understanding metabolic pathways and how long they're going to be active for when designing those types of tests for athletes. So I do want to bring up VO2, and I want to bring this up because this is a very common metric that is used in evaluating the aerobic metabolic pathway. Now I put VO2 with a little dot over the V. And when I put that dot over the V, that's actually a physics notation to indicate rate or how fast something's happening. So in this case, the V represents volume, the O2 represents oxygen. Oh, where's my max? It's on the next slide probably. Max, which is not here right now, is the maximum rate of something, in this case VO2. The dot represents the rate. So without the max listed here, VO2 with the dot is rate of oxygen consumed. And the units that we typically use, mLs per kg body mass per minute, or liters per minute. This is typically referred to as a relative set of units relative to body weight. This set of units is typically referred to as an absolute value. And notice the max is not up here. So right now I have, if I put a mask or I measure how much oxygen I use, that's going to be around 3.5, 4 mLs per kg per minute, maybe a little bit higher because I'm talking, I'm moving a little bit. But that's VO2. And we can measure rate of oxygen consumption for a wide range of movements and tasks to get an understanding of how active the aerobic pathway is. When I add the max on here, there's the max, okay? That represents a single value that represents the maximum rate that oxygen is being consumed, okay? That's not what I'm doing right now. Obviously, I'm operating at a very low rate of oxygen consumption because the intensity of exercise is very low, or the intensity of my movements are very low. But if I start running a little bit faster, start running faster, maybe uphill as well, I start to require more transformation of chemical energy to mechanical energy. I require more force. I therefore need more chemical energy to be transformed over to mechanical energy. And if we're doing that aerobically, then I will have an increase in rate of oxygen consumption, indicating that there's a good link between intensity of exercise and rate of oxygen consumption. When I get to a point where I can't continue, then I've reached my maximum rate of oxygen consumption, and that's what this represents. So VO2 by itself is rate of oxygen consumption, and we measure that for all different activities. Maximum VO2 max, is a single number to represent the max capacity to use oxygen. And the test we do that is a graded exercise test. And we see graded exercise test. Well, a stress test is very similar to this. In a stress test, which would typically be done in cardiac rehab, that's where we would also partner with a EKG. We'd be looking at how the heart is performing during this type of protocol, or we do an ultrasound of the heart before and after this test to get a sense of how well the heart is beating and how much blood the heart is beating with each beat. So graded exercise test by itself typically does not involve that cardiac evaluation. If we're doing a stress test or someone says, hey, I'm going to go do a stress test, that's where they are looking more at cardiac function, and they're doing some additional measures of how the heart is operating. And this test operates just as I described in the previous slide. We started off at a very low exercise intensity, and then we grade the intensity at very specific levels, and then we measure the metabolic demands of the activities, how much oxygen is being consumed, and how much carbon dioxide is actually being expired. And so we can do that on a bike, we can do that on a run, we can do a lot of different step tests, what have you. Hard to do in swimming, but you can do it in swimming. And when we do this type of test, we typically see data like this. On the y-axis is rate of oxygen consumption in mLs per kg per minute. On the x-axis is time. And this is from a bike test. And in the red line is rate of oxygen consumption. And you can see as the test progresses over time, rate of oxygen consumption goes up. That light blue line represents the resistance of the bike. And that intensity is going up. That resistance is going up until the end of the test, and then it goes down to 0. And then this line down here represents heart rate. And there's a nice link between heart rate and VO2. And this is why we measure heart rate during exercise, because heart rate is a good predictor of VO2. It's a good proxy for VO2 when we're out running or biking and we don't have this mask connected to our, we're not breathing into this tube and having a computer analyze the gases that we're breathing in and exhaling. And so heart rate is a nice predictor of aerobic demand during aerobic exercise. All right, and so when we set up a test like this, they are specific to the type of task that we use. Running VO2 max will be different likely than biking VO2 max. Walking protocol will be different than a running protocol. We typically try to get the time of the test between 18 and 12 minutes, maybe upwards of 15 minutes. But we don't want this to be a super long test, nor do we want it to be a super short test. The intensity, we grade it at very specific stages or very specific increments, and each stage is a particular length. Now, one thing I want to talk about, because this term lactate comes up when we start talking about anaerobic breakdown of chemical energy to mechanical energy. And we talk about lactic acid. Now, if you take another class with me, 457, Physiology of Endurance Performance, or 657, the graduate section, this is something I spend a lot of time on. The production of lactate is a really important physiological observation, and it does tell us some really important things. But it also doesn't tell us some things that maybe we have historically been told. Lactic acid is not a poison. It is not a cause of fatigue. In fact, the way that we look at lactate now is that it's a substance that is produced that actually allows the aerobic production of glycolysis or glucose to continue. It's also a fuel. Lactate can actually be a fuel where it's pulled into the muscle, and if enough oxygen is available, can be reconverted into pyruvate, pulled into the mitochondria and used and processed aerobically. So let's say lactic acid is the endpoint of glycolysis. A normal body pH, because we say lactic acid is 7.35, lactic acid does rapidly dissociate to a form of lactate. And it's very hard to move our body's pH off of this number. This is homeostasis. It's really hard. Typically, the lactic acid that's produced during exercise is not enough to really budge this number. But in any case, the terms lactate and lactic acid are commonly interchanged, and I do it all the time. It's a bit of laziness on my part, but lactic acids are very unstable, and it's rapidly converted to lactate. So muscles produce and use lactate. The rate of production increases with exercise intensity. We know that. We can measure lactate by taking a little finger prick, pulling some blood out, and using an instrument to tell us how much lactate is in the blood. And we know that as intensity goes up, the lactic acid goes up. The classic view of lactic acid is that it was associated with fatigue, cramps, side stitch, post-exercise muscle soreness, all this. And part of that was, it made sense. If you take proteins and put proteins into acidic environments, those proteins denaturize, they lose their shape, and therefore they're no longer, proteins are no longer functional. Well, we have a lot of proteins in muscles, actin, myosin. We have the thin and thick filaments, and those proteins, if put into an acidic environment, can lose their shape. That would be muscle damage. However, as I said in the last slide, the acidity environment is not that dramatically changed with the production of lactic acid during typical exercise. So the more contemporary view, as I explained, is that lactate is actually viewed as a form of fuel. That if enough oxygen is used, it can be pulled back into the mitochondria by converting it to pyruvate, and then pyruvate is one of the steps prior to the Krebs cycle, which ultimately ends up leading to production of ATP. So something that is really common to look at when evaluating both the aerobic and anaerobic metabolic pathways is to look at the lactate threshold during a graded exercise test. And this threshold exists, it's real. It's often disagreements in terms of how to actually identify it, but it is a phenomenon that does happen. And it is the point where during a graded exercise test where there's a systemic increase in the lactic acid concentration, how much lactate is in your blood. The basis of this concept is that this point signifies when ATP is being generated to a greater extent anaerobically versus aerobically. All right, I'm going to spend a little bit more time on explaining that statement. Therefore, this point is also referred to as anaerobic threshold, ventilatory threshold, or even onset of blood lactate accumulation. Each of these are sort of unique in their own world, but they're all trying to signify where the intensity of exercise that the anaerobic system really starts to kick on. All right. Ventilatory threshold is typically determined using gas exchange, VO2 and VCO2. Onset of blood lactate accumulation is a little different in that you're setting an absolute number of blood lactate that if you go above it, then that signifies some physiological response. But these are all used to represent or try to identify how active the anaerobic pathway is during an aerobic type exercise. So this plot is important, and if you take Physiology of Endurance Performance, I actually spend a lot of time on this plot, on this figure. There's 4 plots here. This first plot right up here is the typical data we would see of blood lactate on the y-axis during a graded exercise test, and there we're showing running speed from 10 kilometers per hour up to 20 kilometers per hour, and it's a graded test. And so what happens is during that graded test, the speed gets faster and faster and faster, and we're measuring blood lactate at different points. And then at some point, the speed is reached where that blood lactate starts to increase. And it really skyrockets towards the end of the test, and then the person stops running. And so one thing that people have identified is that there's this baseline level of lactate that's in the system, and then it starts to increase, and where this point increase is identified as the lactate threshold, aka anaerobic threshold, what have you. But what's really interesting is that if you do a finger prick right now, if you're watching this video, and we put that blood into a lactate analyzer, you will have lactate in your blood. Okay, and even if you start moving around a little bit, and you do a finger prick, you're probably, and do another test, you're probably gonna have about the same amount of lactate, okay? And so what's interesting, lactate's always been present. The anaerobic system is always on, as is the aerobic system. We're always using these two systems at the same time. It's just how active each system is. And so even though there's not a rise of blood lactate in the blood, the anaerobic system is being engaged more and more and more. And that's what this plot represents. This is blood lactate, or this is lactate, okay, on the y-axis, and this is the same test. And there's two lines presented here. The top line is the amount of lactate being produced. The bottom line is the amount of lactate being reused or buffered. So once lactate is produced, we got a couple of things that can happen. One, it can be buffered, meaning it just the acidic nature of it goes away, and we actually just a process. The chemical steps is we just exhale more CO2. Another fate of lactate is oxygen's present, a certain coenzyme is present, it'd be converted back into pyruvate and it'd be used as a fuel. And so there's this interplay between producing lactate and buffering and or using lactate. And so this top line is lactate production, bottom line is lactate use or removal. And you see that top line is increasing. The amount of lactate being produced during the graded exercise test, even at these lower speeds over here, same test, the lactate is being increased. What's also interesting is the amount of lactate being buffered and or reused as a fuel is also increasing. And so really the amount of blood lactate that we measure through a finger prick or an earlobe prick or what have you is the difference between these two lines. And you can see that the difference between these two lines is constant. These two lines are parallel to each other. The amount of lactate being produced is the same as the amount of lactate being buffered or reused. The anaerobic system is increasing in activity during this phase of the graded exercise test. But at some point, we reach an intensity that the lactate production starts to exceed the amount of lactate that can be buffered and or used. And that's where we see a divergence of those two lines. And then the amount of lactate in the blood is the difference between these two lines. And these lines are getting further apart, meaning blood lactate actually goes up. And so two things. One is anaerobic system, even in this test where blood lactate levels is steady, the anaerobic system is has to be more active during a graded exercise test. But at some point, the second thing, at some point, the amount of lactate in the blood starts to increase more because there's a greater production of lactate versus how much lactate can be buffered and or used. Okay, so really important concept for lactate and what it tells us about the anaerobic system. This is not a threshold, this is not an on-off point for the anaerobic system. It's off and then all of a sudden it's on. That's not the case. The anaerobic system's always active, it's just how active is it. These other two plots are just a little different perspectives of what's going on. This is blood lactate, same test, and now just representing this obla concept that, well, maybe we're interested in the absolute amount of lactate that's being produced. 4 millimoles is a common number. 2.5, 3, or even 2 millimoles of blood lactate is common. But obla is a little different concept, but it's still trying to get a sense of how active the anaerobic system is. This is an interesting plot. This is different than these three right here, in that the x-axis is a longer period of time, and this is blood lactate. This is just some test at 18.75 kilometers per hour, 18 or 17 and a quarter kilometers per hour. So this is a slower run, this is a faster run. And they just did blood lactate measures throughout the 25-minute run. And what's interesting is, at the faster speed, blood lactate continued to increase through that endurance run. The anaerobic system was active, so much so that the blood lactate production was exceeding the amount that was being buffered and or reused. But they still did 25 minutes. When running at the slower speed, this is really interesting. Blood lactate went up at first, and then it actually started going down near the end of the 25-minute run. That's an indication that blood lactate levels that were being produced were actually being exceeded by the amount that was being buffered and or reused as a fuel. So lactic acid was actually being pulled back into different muscle cells and reused as a fuel. And running at this speed, blood lactate produced matched the amount that was being buffered and or reused. So really interesting concepts when we start looking at, this is a non-graded exercise test. This is just a submax test at 3 different speeds. But hopefully this gives you a sense that lactic acid by itself is not an indicator of fatigue, and it does help us get some insight in terms of what's happening with the anaerobic system, but we need to be careful to understand that the amount of blood lactate that we're seeing in the blood represents the amount of blood lactate produced minus the amount that's being reused. All right. Okay, so lactate and exhaustion. Just an interesting point. If lactate is infused into the bloodstream, it actually has no noticeable effects. It's important to prevent a buildup of hydrogen ions. You don't want to get acidic in the body, but lactate is very easily buffered. And that's why lactic acid is buffered to lactate. Lactate levels are not necessarily high after a prolonged exercise. So just as an example, if we go to a marathon and we start finger pricking everyone at the end, at the finish line, and we check their blood lactate levels, may not be high, but they may be exhausted, okay? So it's an interesting phenomenon that you can do a marathon, but not necessarily have a high blood lactate level. So it's just something to keep in mind that lactic acid, we just need to really shift our focus that it does tell us something about the anaerobic metabolic pathway, but we need to be careful about how to use that information when we're dealing with sports science. All right, so summary, we talked about different forms of energy, and calorie is a unit of heat. Oh, I should have mentioned, I'm sorry, another way to measure how active the energy system is to put someone in a special room that can measure how the room temperature changes during exercise. And that actually is a measure of the heat given off of the person, which tells us, again, how active the metabolic pathways are during exercise. That's a very different way of figuring out calories, and that's a direct calorimetry way to measure metabolic pathways versus an indirect, which is what we do when we measure VO2. We're measuring gas exchange to ultimately understand how active metabolic pathways are. Talk a little bit about fuels. This is our extent of how deep we'll go into nutrition, at least from me. When we get into the nutrition section of this course, I'll bring on someone who has much more expertise in this area. But looking at carbohydrates, fats, and proteins as potential chemical energy. We talked about metabolic pathways, anaerobic and aerobic, and talked about VO2 max versus just VO2. And I am lazy. I did not put the dot over that V, and I went in a little bit more detail on lactate. I hope this is helpful, this big picture perspective of exercise physiology and how we can ultimately bring this information back to understand sports performance. Thank you.